So hi, today I would like to solve example with the Flyback, but today I don't have the camera, so I will just use it using my pad. Anyway, so it is the same Flyback converter with the previous example. So again, this is example 7.3 from Hart, and it is the same Flyback converter. Let me show it just to remind, and I am continuing with the same PDF documents on solving. So in that version, remember, we had like 24 volts input voltage and 5 volts output voltage, and our load, okay, our load was 5 ohm resistance. And now in this problem, the load resistance is increased from 5 ohm to 20 ohm. So basically we will draw less current. And again, if the minimum value in the LM reaches to 0, then that converter starts working in the discontinuous conduction mode. And actually the question asks us show if the converter works in the discontinuous conduction mode, and also find the output voltage. And by using that problem, I would like to derive equations and make the discussions for the discontinuous conduction mode. So let's do the calculations, and let me put the waveforms here, and let's see what happens to our output power. So in the previous example, we are drawing, remember, 5 volts and connected a 5 ohm resistance. So our output current was 1 amps and our output power was 5 watts, and we were trying to find what is the average of the IS power, IS current, assuming it is like 100% efficient. So let's do the same thing and assume continuous conduction mode. So let's see our now P or R out is equal 20 ohm. Okay, so you can calculate if it is DCM. Okay, so I out, it will be the same voltage, okay, the same voltage, but the output current will be 5 divided by 20. Okay, it is 0.20 25 amps, right? Or I can calculate P out as 0.25 amps times 5 volts. Okay, so you can find it like 1.25 watts, of course. So now our output power actually decreased from 5 watts to 1.25 watts. Okay, so let's do the same calculation, and remember, I am just drawing current from the source side whenever the switch is on. Okay, whenever the switch is on. So that's why, in order to calculate the average source current, I need to use that one, okay, with the duty cycle. Actually it is the average, but I would like to find the IL min plus IL max divided by 2 if I would like to find that value, right? So again, let's do the same thing using the new numbers. So let's do the calculations here. So again, let me calculate the IS average. Okay, IS average will be, I am drawing like I have 24 volts here, and I assume the same output power is going to be drawn from the input. It's not 5 watts anymore, but it's 1.25 watts. Okay, 1.25 divided by 24 is our average current. Okay, and actually if you calculate it, I think it's around 52 milliamps. Okay, but again, this average is this is the source current, and this is the all average. What I want to find is that value. Okay, so I want to find IL min plus IL max divided by 2, or IL average, in other words, like the same we did here, and that one is equal to, you know, the average source current divided by the duty cycle. Okay, so you can find IL mean plus IL max divided by 2, okay, is equal to IS average divided by 0.385, the same duty cycle, and if you calculate that, it is around 135 milliamps. Okay, so I want to find the IL mean. Okay, IL mean is IL average, which is that value, minus delta IL divided by 2. And actually let's use the same delta IL, okay, same delta IL, and the inductance are same, you know, the switching frequency, everything is same, so I will use exactly the same value in order to find the minimum value. Remember, in the previous example we subtracted the half of that ripple from the average current, and it was 310 milliamps, and it was larger than 0, so it was working in CCM. So I will do the same thing. So 135 milliamp minus 460 milliamp divided by 2, and it is minus 95 milliamps. Okay, so it is less than 0, and actually it is not possible. I will tell why it is not possible. It is working in DCM. Okay, why it's not possible? Because let's have a look at the circuit here. So during the charging period, you are closing the switch and your LM is, you know, increased and it is being charged, and actually we are looking at that part. It is the end of our duty cycle. So actually during that part, that current is being sent. Okay, the same current is being sent, and you are charging your capacitor and also supplying your load, and then that current is going down and down. Okay, but you know, if you just look at the sign convention, actually whenever this was flowing that direction, you have negative current, I mean, or opposite current in that way, and you still have current in that path. But if that direction, that current direction changes, if it would like to flow, let me use a different color. If you would like to use, you know, that kind of current, which is the implication that reaches down to negative, like minus 95 milliamps in our case. Okay, so that implies, you know, if you just look at the sign convention, you need to draw some current in the opposite direction. But in that way, you know, you will have the diode reverse biased, and it will cut the circuit, and there will be zero current here, so there will be zero current here, so there will be no voltage that's to run the LM in the negative direction. So whenever it reaches to 0, okay, whenever it reaches to 0, it will stay there, and the diode will be reverse biased. So let me get the waveforms here and do the rest of the calculations. Okay, so the current waveform will be more like that, and this is DCM. Okay, so it's similar to what we have seen in the first semester. So actually, if it is DCM, you are working with zero current, and charging characteristics and its duty cycle, it is same. However, while you would like to go that way, I mean, if it were all, you know, CCM, so your circuit would like to have, you know, that kind of going down, and that is our minus 95 milliamps here. But again, due to diode, so you are, you know, discharging. So at that one core, B core is actually equals to 0. So the core, you know, completely demagnetized, and your current in LM reaches to 0, and it stays there. So actually it stays there until, you know, that part, and during that part your I mean, remember in the previous case we were supplying whenever we are charging that inductance, that capacitor is supplying the load. So whenever we are turning off that switch, and now that inductance current is charging the capacitor, but now that amount is shorter. Okay, the amount is shorter because our current in the LM is actually, you know, comes down to 0 quicker than like 1 minus DTS. So obviously that will affect our output voltage, and let's try to, you know, calculate the main parameters, and let's try to calculate the output voltage. I know that is 0, so let's try to find that value. Okay, so this is ILM max, and of course, you know, that is 0, and again while the switch is on, that one is charged with Vs, so I can write ILM max. Okay, ILM max is equal to Vs, okay, times that period d time Ts divided by Lm. Okay, so it is the same value, and let's write it here. In discontinuous conduction mode, ILM minimum is equal to 0, right? There are a couple of different derivations for the output voltage here. Let me add another page to here. Oops, just a second. So let's drive it using the. So okay, I can say my source power is equal to my output power, right? So I can write Vs times Is, you know, average over that range. That will be equal to V out square divided by R, and I think we already, you know, calculated that one. But I mean, the important thing is now that output current. I mean, you shouldn't use that one, because what we are trying to derive is, I mean, this one we assumed the output voltage stays constant, and we assumed the output voltage is 5 volts, but at the end of the day, you know, we need to get a minus ampere to have that power relation. So we shouldn't again use the same power, but instead we know how much power is taken from the source, and we can calculate that one to find the output voltage, right? So that current is 0, and that current is ILM max. So the actual power, let's use the orange one, so you are drawing power. Okay, so this is the power drawn from source. So I need to take the average of that thing over, you know, that period, or you can go from the energy if you want. Then the output voltage, if I assume it is to be constant, if the capacitor is large in the steady state, I can find that value. Okay, so that is the trick part. So I can write the average like P source, right? You know, that area, it is, remember, this is I need to multiply that one with voltage, and that gives you the power. So if I integrate power, that is giving the joule, and if I divide it over that period, again I will find the average power. So it will be 1 over 2, okay, ILM max times dTs, that orange area, divided by Ts, will give you your average source. So again, in the book it was written like using the other parameters, so let's use that parameter here. So I can write 1 over 2, okay, Vs times dTs, okay, divided by Lm. You know, that dTs is for the current, and that Ts is for that integral over there, and that one is to find the average T. There are lots of dTs don't get confused with that one, and actually that one and that one gets cancelled out. And sorry, I think I need to multiply here by Vs as well. So this is the current. I need to find the source voltage times Vs. Okay, so this is the like average source current. So this is source voltage that is constant. So all of them gives us the average source power, and that will be equal to VO squared divided by R. So this is my output power. Okay, so if you just write everything in terms of Vs and actually duty cycle, what you are going to find is like VO is equal Vs times duty cycle times T times R divided by 2 Lm. Okay, D square, I have D square, it was taken out. R comes to here 1/2, and there's all a square root over that one. Or again, you can write that one as like Vs D times square right R 2 Lm frequency. Okay, so this is the output voltage in DCM. So let's have a look at how does it changes with the same duty cycle. So for our question, let's put out the parameters. Vs is equal to 24 and duty cycle is 0.385. Square root resistance is 20. 2 times 500, I think, microhenry times switching frequency was 40 kilohertz. Okay, and if you do that, you will find 6.53 volts. Okay, so output voltage, remember in the previous one, increased from 5 volts to 6.53 volts. Okay, so what you need to do, again, we had the same relation in the buck or boost converters. So actually, if you keep the duty cycle same, and if the converter gets into discontinuous conduction mode, then you will have some increase in the voltage. So what you need to do is you need to have, again, that is what the controllers are for. So you need to get some feedback from here. So you will have a controller controlling the duty cycle. So whenever the converter gets into the discontinuous conduction mode, so the voltage starts climbing up. So your controller should detect that one and start reducing duty cycle to get the same output voltage. Okay, so again, if you think of that one, and I strongly advise you to read the application notes for the Flyback controllers, that may probably will be selecting those things for your hardware projects. The good thing is, like, once you have zero current here, all the transformer current, okay, will be zero. So you can have like reduced core losses, or at least the period has reduced. So that is a good thing. And secondly, actually, when you are in that cycle, okay, when you are turning on and off your transistor, okay, so if it were a continuous conduction mode, okay, so if it were here, so you are turning on your your switch while the inductor current is that much, okay, or you are turning off your switch again when the transformer or LM current is at that point. Okay, so you will have increased switching losses. However, if you are working in the DCM, okay, so your ILM actually came down to 0 before we turn on the switch. Okay, so the switch, it will be like soft switching, so it will pick up from 0 volts, so you will get rid of those switching losses. Okay, that's a good thing. And again, you know, similarly you can think the same thing for that diode as well. Okay, so remember, whenever I am turning on that switch, that diode is turning off. Okay, so while that one is turning off, so you will have reverse recovery losses, remember, during that instant. Okay, so in that instant when the, you know, that one is maximum or here, so your diode is having some switching losses as well. So having the current 0 before that transition occurs is actually also good for your diode losses, and actually that is also why, especially in small flyback converters, the DCM can be a good thing, and it will, at the end of the day, it will result in a higher efficiency. And there are like controllers actually can automatically switch from DCM to CCM depending on the operating conditions, because at the end of the day, depending on your, again, voltages and current levels, the load currents or the resistance of the load is not under your control, so you need to compensate for that voltage transfer changes. Okay, the ratio changes, so you need to have some kind of a closed control loops. Okay, so that's all for today. Okay, thank you.